Right, let's talk about RESNET. So RESNET is a typical convolutional neural network based network. This network I think has various forms based on the number of layers in the network, and that's how the versions of this RESNET has a suffix that indicates the number of layers. So here RESNET 50, for example, it stands for a deep neural network with 50 layers deep. And ResNet is also a short name for residual networks. So this network has been trained on pre-trained on the ImageNet dataset that consists of data from 1000 categories like keyboard, mouse, pencil, and many different animals like elephant, tigers, cheetahs, rabbits, tigers, dogs, cats, and things like that. So this network won the first place in ILS VRC 2015 competition, where uh, 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 lots of different companies like Google, Facebook, Nvidia, and a lot of researchers from the industry participate in that competition and try to produce a deep neural network architecture that can classify an ImageNet dataset with the highest amount of accuracy. So ResNet 50 was found to be the most accurate in 2015 ImageNet competition, and that's why it's very popular. Let's understand typical problems in the neural networks, deep neural networks. So as you know, the deep neural networks is nothing but it's a cascading of convolution layers, pooling layers, then input layers, and lots of hidden layers, right? So as we increase the number of layers in the deep learning network beyond a certain limit, what we observe that the accuracy starts getting degraded, right? For first few layers the accuracy improves, but as we increase the number of layers in the network, the accuracy suffers, right? And the major reason for that is the problem of vanishing gradient. So just to give an example, so when you are connecting nodes from one network to other network, the weight gets each of the nodes output gets multiplied by a weight we usually call it as W, and W is usually less than 1. So as you keep cascading the inputs through the multiple networks, anytime you multiply it with a value less than 1, the value keeps decreasing, right? So eventually you get to a point where the value becomes so small that it stops to have significant impact on the network, and sometimes it also degrades the performance of the network. So this problem is called the vanishing gradient. In case where the weight is more than 1, the eventual effect of cascading the layers is the value of the multiplier will this value of the weight will keep increasing, and the value becomes too big as we increase the number of layers. So this is called an exploding gradient problem, right? So as we grow the number of layers in the deep neural network, we have this problem of exploding and vanishing gradient, right? So that is what we need to avoid. So here is a example of how deep learning, deep neural networks sometimes above a certain limit in fact are worse than the shallow neural networks. So on the left you see a training error for a 56 layer deep network is worse than the 20 layer network. So this is during the training of the network. Then once the network is trained, even when we submit a test data, we observe that the test error is also worse on the plain 56 layer vanilla neural network as compared to the 20 layer network, right? So that is what it has been observed. So to counter this issue, whenever we are building a deep neural network, what is done is, so usually in any deep learning network you will see this pattern. You have an input, you have weight, we multiplied by that, and we pass it through a nonlinear function like ReLU, and then we get the output and we keep cascading, right? So this layer is present, but in case of ResNet, what we do is, in addition to adding this normal forward propagation, we also add a partial input. We skip that and we take a partial part of the input and we add it to the final output, right? So here the final output is not only function of linear weighted input but the actual function of direct input also. So this is called a residual block in case of residual neural network. So this introduces a dependency not only just linear combination of inputs but the actual inputs also, and that is what avoids the vanishing and the exploding gradient problem in the deep learning network, right? So this arrow which is coming directly from x2 output is called a shortcut connection, or also called the skip connection residual block, and this is what is a building block of a ResNet 50 network. So once the test was performed, again on the left you see a plain vanilla network performance. As you can see, the 34 layer plain vanilla network errors are worse than the 18 layer network. But on the right, when you build a deep learning network using the ResNet 50 architecture, where we have those skip connection blocks that we saw earlier, the ResNet 34 layer performs much better than the ResNet 18 layer. So that's the crux of it. If you want to build a deep learning network, ResNet 50 is the way to go. So here is the architecture of the ResNet 50. So this is the layer at the top. This is a typical convolution layer, right, with the different sizes of filters, like 64 by 64, then 3 filters, 1 for each color, RGB. Then we have a max pooling layer, average pooling layer, and finally softmax, right? Typical neural network, but it uses a residual building block in case of, instead of using a normal convolution block. So here is the comparison between the ResNet and the other popular deep learning networks. So ResNet 50 is down here. As you can see, the ResNet 50 layers, the top one error percentage and the top 5 error percentage is much better as compared to the other flavors of ResNet 50, the fewer layers, and also as compared to the Inception, VGG, and the GoogleNet itself, right? Much better performance than VGG and GoogleNet. But of course, as you increase the number of layers, you still can get a better accuracy, but then you might trade off in terms of memory size of the ResNet. So that's all about the ResNet 50 network.